So let's imagine this case. We have to define, we are going to talk a little bit about the search space and global optimum. And probably if you are taking the operations research class, optimization is not a new term to you. You already heard about the optimization. So optimization is very tightly linked to the space search. For example, let's imagine that we have two values here, x values here and y values here. If this was structured like this fashion, called x and y, and we have this idea of utility and this idea of the utility, all the constraints, and this is our viable solution. If we fall into here, then it's maximize is valid choice, and if this is in the outside, it's not going to be valid solution. So we are going to keep looking into this area, and our reward is going to be structured in this way. And a certain point, there is a optimizing point that maximizes our reward. That's the basic structure of the linear programming, right? However, let's imagine that we have all these areas are viable. So these all areas actually fall into the constraint area. So we can choose any points here, but the reward structure is not linear like this. Reward structure is structured like this, right? This is being called contour map. In Korean 등거선, and in this contour map, these areas actually has a high value, and these areas have a lower value, right? And how to find this area? Actually, this constraint satisfying space, we are searching through this space to reach to this certain location, and that is being called search space search or search space. This is the search space, and the search is going to get into here from somewhere else. Similarly, you want to find the highest point here when we have this all viable. Viable means valid search space. Let's imagine that we have finding maximum problems in a binary search tree. And in this binary search tree, this is going to be the search space, the tree itself, and finding a maximum point. Maximum value is going to be global optimum, maximum value, and finding a maximum traveling to the right hand side is going to be the search procedure, right? And data structure is a kind of safe passage to a consistent keeping the assumptions. If you just keep following the right hand side, then there is a guarantee that you are going to reach to the maximum value. However, if the search space is structured in this way, and if your root starting point is somewhere here, you don't know how to get to this point. You may just follow here like this, like this, like this, and if you are very lucky, you may be able to get to this point. But if you are misguided, then you may just follow this way, and you may find this point which have the second maximum value. It's not the maximum value that we want to find, it's a secondary value, right? However, there is a case that this might look very good choice and you just stick to it. So that is being called local maximum. Okay? And there is always case there is always case that you can fall into this local maximum if the search space is not structured nicely as the binary search tree. Okay, I'm just gonna erase it a little bit. Okay, the searching a record by record is really not feasible. So for example, if you're just going to cover this whole area, it's going to be x multiplied by y case. What if we have another variable, it's going to be z? What if we have another variable, it's going to be a multiply b? And this is really unacceptable. This is going to be a huge cost. So searching a record by record is not a feasible approach. So, and this is not this list of values. So certain level is going to be a lower value, certain level is going to be higher value, and if you just keep following the up, or if you just keep following the right, there will be a bigger value. There is no such pattern in this search space. So it's going to be a very difficult. And eventually you will find out there is no deterministic ways to search the space. Means that in binary search tree, if you just keep following the right hand side, and if there is nothing, then this must be the maximum value. And it's very deterministic way of searching. There is already set a method approach and you just follow it. However, in this case, there is no certain way to travel from down here to up there. There is no specific way to get this. There are very diverse ways to get this, and there are even cases that might look similar to the highest value, but ends up being at the secondary value. There are certain cases to that. So there are very randoms, and it's not being controlled with the data structure. And with this search space, not like this nice structured search space, this case is really unstructured search space, and you want to find the maximum out of it. And that's one of the difficult problems. You see this multiplications over variables, and that is very similar to this n factorial, right? This multiplications way. And this kind of the really unstructured case, to navigate through, we might have to do the n factorial searches, and actually that's the perfect applications of the genetic algorithm. Sorry. Okay. Oops. So that's why I'm talking to you about this search space at this slide set. So for example, one way to do the search is that finding maximum with the binary search tree and this unstructured search space. One way of searching is that here you can just keep looking at the right hand side, keep going that. However, with this search space, you might go this way, right? So if you just follow the higher value, in that case, you might end up being at the second location, which is not the place that we are looking for. We are looking for here, right? Follow the higher neighbor until the search hit the no way to go. So this is the highest neighbor. If you just keep following the highest value, it's a little bit higher, then you are going to sit on here. And That's being called hill climbing heuristics or gradient ascent heuristics. From here, you are just finding the maximum neighbor. You are just finding the maximum neighbor and ends up being at the maximum value. If search space is very nice, you can just follow this way. However, if search space is not nice, in this case, you are very likely to end up at the secondary location. Okay? So problem is that you might end up being here. So, okay, that is the highest price around the search, but it's not the highest place in the entire map. The highest place is here, and you want to get there. So that's being called as falling into a local optimum. So this secondary location is often called local optimum. That means that it's only optimum in this local area of search space. If you just see the global area of the search space, there is a better value, and actually that is the value that we want to find out. Okay? So it means that you have to take a little bit of hit. Hit means the reduction of values. So here in this case, never visit the lower value, right? However, in this case, there are some cases that you might have to visit the lower value to pass through and to get to the global optimum. Means that you might have to endure the reduction of search values for some time, but you have some kind of belief that this might lead to a really bigger values in the eventual. So that is the assumptions that we make in this global optimization search. So here, the local optimum is actually same to the global optimum. However, here, the global optimum is not equal to the local optimum. Okay. So why does hill climbing have a trouble of falling into a local optimum? Because it afraid of getting into a lower value. There might be a bigger value over this valley here. So this, if you just see this as a 3D image, this might look like this, right? So there is a really high mountain here. There is a small hill here, and you are starting from here. If you just follow the bigger value, higher place, you might end up being here, but that's going to be local optimum. However, you might have to endure going down a little bit, and then after going down, you might have to go up a really higher, and you are going to go up really higher, and eventually you can get to the global optimum. So it means that you might have to endure some of the going down approach if the search space is really not structured nicely. Okay. So hill climbing, if you just keep following the bigger value, there are very likely chance that you fall into the local optimum. So you might want to have another heuristics to solve this problem. Another types of the algorithms to solve this problem. So we are talking about the heuristics here. So heuristics are actually types of the algorithm, a type of algorithm that might not produce the exact solutions, but can result in a very close solution. That is being called heuristics. There is no proof that it can get to the maximum point, but it can result in a very similar solution to that maximum solution. If that is the case of the algorithm, then we call it heuristics or heuristic algorithm.